In this module, we shall able to know about the physical properties of the glass, which actually makes the examination of glass very easy for the forensic investigators. And then we will also study about the different types of glass fractures, which actually is going to tell us the direction of impact. Basically, the value of glass fragments as evidence is not always fully recognized. Windows, automobile glass, broken bottles and other glass objects actually can serve as very crucial evidence in burglaries, murders, hit and run cases and many other cases which involve huge crimes. It is actually known that if there is any person who is standing very close to the place where accident or the crime has taken place and a glass has broken, then there is a tendency that the fragments of glass, those broken glass, can be actually found out on his clothes and shoes. Consequently, the clothing or the burglary suspects, in case where windows have been broken, they will often retain some very small microscopic glass pieces or glass fragrance. As a result of hit and run cases, for example, headlight lenses can be broken very less times, but very less often, but very common. There is also a possibility of breaking of windshield glass. Therefore, both the scene of the accident as well as the clothing of the victim can be expected to be sources of glass fragments. Now, basically, the knowledge about the physical properties is actually very important, as it makes the examination of the glass easier for the investigating team, since glass is frequently encountered in various crimes such as burglary, road accidents, murders, sexual assaults, shooting incidents, etc. For example, the pieces of broken glass from a glass window or glass door may stuck in the suspect's shoes or his garments while committing the crime, or pieces of headlight glass of suspected vehicle may be found at the scene of hit and run case, and it can thus act as very strong clues to confirm the crime. Thus, we can say the glass forms one of the most common evidentiary materials in many criminal investigations. First, glass fragments can be recovered from the suspect, which is more frequently actually achieved through shaking or brushing the garments very hard. The resulting debris is observed under optical microscope and glass fragments can be then manually separated. The physical and the chemical properties of the recovered fragments are then determined, often through glass refractive index measurements and other instrumental methods of elemental analysis. Forensic glass examination has actually is a well established analytical pathway. First, the glass fragments are recovered, observed and then identified by microscopy. Then refractive measurements of a portion of these fragments is performed, and these measurements are then compared to the measurements taken from a control sample. If they match or otherwise appropriate or approximately match, further elemental analysis of these fragments take place, which actually leads to the person who has actually committed the crime. A wide variety of techniques exist for elemental analysis of glass. Most of these techniques are classified as scanning electron microscope or energy dispersive X-ray spectroscopy, electron microprobe analysis, inductively coupled plasma mass spectrometry, or laser ablation inductively coupled plasma mass spectrometry.
Physical properties of glass. A brief review. The study of the physical properties of the glass offers a direct means of recognition of the glass fragments found at the crime scene. If the fragments are very small, it forms the basis of identification. These properties are constant for a glass of definite and consistent composition and are useful for investigation. The variations in the composition of glass cause variations in the physical properties from one glass object to another. Some of the physical properties of glass are as follows. Density. The density of each substance is the mass per unit volume of the substance at a specified temperature. Its units are grams per milliliter or kg per liter, where mass refers to the amount of matter in an object independent of gravity. It is an intensive property of matter that remains constant irrespective of the size of the sample. It is considered as a characteristic property of glass and is thus used an aid in identification of the sample of the glass involved in the crime, as different types of glasses like window glass or headlight glass have got different densities. The density of the glass pieces can be determined either by flotation or density gradient method. Refractive index. Light waves travel with a constant velocity until they pass through another medium apart from vacuum, such as glass, where at the point of contact the light bends and suddenly slows down. This bending of waves because of the change in the velocity of light is called refraction, while the ratio of speed of light in vacuum to the speed of light in the medium or substance like glass is called the refractive index of the substance. That is, N is equal to C by V, where N is represented as the refractive index, C is the velocity of light in vacuum, while V is the velocity of light in the substance. It is also referred to as a ratio of sine of angle of incidence to the sine of angle of refraction. Refractive index is a function of chemical composition and atomic arrangement. In glass, these are controlled by the composition of the batch, chemical composition, and the cooling history of the glass, atomic arrangement. Tempering changes the cooling rate of the surface of glass relative to the interior and imparts a continuous change in the refractive index from the surface to the center of the glass. Refractive index is the most commonly measured property in the forensic examination of glass fragments because precise refractive indices can be measured rapidly on the small fragments typically found in casework. It can aid in the characterization of glass. It provides good discrimination potential. Refractive index varies with wavelength of light and temperature. This property also characterizes a substance and is thus useful in its identification. Different types of glasses, like television glass 1.49, window glass 1.51, etc., have got different refractive index which makes possible their identification. The refractive index varies with the wavelength of light and also with temperature, which makes possible its measurement by the immersion method. Dispersion. All transparent objects like glass slows down the shorter wavelengths of light more than the longer wavelength, and thus the refractive index is higher for shorter wavelengths than for longer wavelengths. This process is called dispersion. In other words, the splitting of white light into its constituent colors when it passes through a transparent object like a glass prism is called as dispersion. The coefficient of dispersion is expressed as a change in the refractive index between two specified wavelengths. Color. The color is used for identification on the occasion when the glass fragments involved in a crime are colored. For example, decorative glasses or bottles. Even the glasses that seem to be colorless have been found to have some tint. Hence, when the fragments of glass available are large, their colors should be compared. Ultraviolet fluorescence. Although most of the glass samples don't show the property of fluorescence or show little fluorescence, some types of glass fluorescence with colors which may be blue, violet, brown, purple, or green when examined in ultraviolet light. Thus, in some cases, it becomes useful in distinguishing between different glasses. Hardness. Since glasses vary appreciably in hardness, this property becomes actually useful for differentiation between different glasses. Types of glass fractures or fragments. Most of the strength of the glass is in its surface. Glass has less tensile strength than compressive strength. So, the glass bends to any force which is exerted on any one of its surface. But the glass breaks due to tensile stresses that pulls the surface of the glass apart and hence exceeds the elastic limit. Imperfections, flaws, or minor damage in the surface of the glass, such as scratches, bruises, or etching, which we call as glass fractures, reduce the tensile strength at those points in the surface and hence reduce its tensile strength. The study of the glass fractures gives a lot of information about the crime. For example, a fractured window glass will reveal information that can be related to the force and the direction of an impact, which is useful in reconstructing the crime. When there are a lot of pieces of glass in a sample, it is advised to assemble them to know whether the glass fragments come from one or more than one object, which can reveal the brand or the pattern of the original object. A glass that has broken while committing a crime shows primarily two kinds of fractures, that is, primary or first made fractures and secondary or subsequent fractures. Primary fractures are called radial fractures, while the secondary fractures are called concentric fractures. They look like the spokes of a wheel as they radiate towards from the point of contact. Concentric fractures forms a series of broken circles or arcs around the point of contact. They are as follows. Radial fractures. Radial fractures are produced on the surface opposite to the one where the force had been applied. When an external force is applied on one side of a glass, then the glass sheet bends away from the force so that the tensile stresses are set up in the opposite surface of the sheet, while the compressive stresses are developed on the surface to which the force has been applied. If the applied force is so strong to have exceeded the elastic limit, the glass breaks, invariably from a point where a tensile stress of sufficient magnitude has developed. In a glass sheet, the primary or the initial rupture, which we call as radial fracture, tends to be star shaped or appears like spokes of a wheel. In other words, it spreads from this point of contact as a series of cracks in a number of random directions as shown in the figure. For example, penetration caused in the window by a projectile or a bullet produces a pattern in which crack radiates outwards and encircle the hole. Concentric fractures. But if the force continued even after radial fracture, especially when the instrument is either blunt or tapers abruptly, there is bending movement that causes tensile stresses to develop on the side of the glass to which force was applied. This leads to a series of cracks known as concentric fractures which connect with the adjacent radial fractures. The concentric fractures form a series of broken circles or arcs around the point of contact. Other types of fractures present in glass. Low velocity impact fractures. Low velocity projectiles produce cracks in the glass, which radiate outwards from the point of impact, radial cracks. If a pane is firmly held on all sides, concentric cracks can form around the point of impact. The sequence of multiple impacts can be deduced when the cracks caused by a subsequent impact terminate at previously formed cracks. By observing the Wallner lines ridges on the radial cracks, the direction of braking force can often be determined. Observe only the Wallner lines on the radial cracks nearest the point of impact. If the impact site is not preserved, the glass must be reconstructed. The original orientation of the glass must be known to complete the determination. The ridges, Wallner lines, on radial cracks nearest the point of impact are at right angles to the side opposite or to the rear of the impact. This phenomena is referred to as the 4-hour rule. Ridges on radial cracks are at right angle to the rear. The 4-hour rule is unreliable for laminated glass, tempered glass, and small windows tightly held in a frame. High velocity impact fractures. A high speed projectile striking a piece of glass will produce a cone or crater. If the projectile passes through the glass, the opening on the exit side will be larger than the opening on the entry side. If the impact site is not preserved, the glass must be reconstructed to observe any coning effects. However, because of the small size of the shattered fragments at the impact site, the reconstruction of a sufficient portion of the objects to display coning effects may not be possible. The size of the hole and the diameter of the crater cannot be used to reliably predict the size of the projectile. Projectiles that pass through the glass at an angle to the surface produce an elongated hole. Radial cracks may also develop from high velocity impact. The sequence of multiple impacts can be deduced when the cracks caused by a subsequent impact terminate at previously formed cracks. Thermal fractures. In non-tempered glass, a typical heat crack is curved, has a smooth edge, and has no indication of the point of origin of the crack. Localized heating of thick pieces of glass can cause cracks with a feathered appearance. The side to which the heat was applied cannot be determined from fractured edges.
Now let us summarize what we had studied in this module. Basically, what we have come to know is that glass now serves as one of the most important, that is, major evidence on the crime scene. The knowledge of the physical properties of the glass, they also act as a valuable source of information for the forensic investigators. The examination of the glass can actually help to reconstruct the crime by knowing the source of the force that has been responsible for breaking the glass under consideration. The study of glass fractures actually gives a lot of information about the crime. For example, A fractured window glass will actually reveal the information that can be related to the force and the direction of impact, which is very useful in reconstructing the crime scene. A glass that has broken while committing a crime shows primarily two kinds of fractures, that is primary or first made fractures and secondary or subsequent fractures.